Welcome back to video number 7 in my introductory series on data science using R. I am your host, David Langert, and I am proud to announce that after too long of a delay, this is the final video in this series. So those of you who have been posting on YouTube about when I was going to make the next video, here you go. Here's the final one. What we've got here to start with is my R Studio environment, which has executed all of the code up through the end of video 6, which I would highly suggest getting off of the GitHub associated with this video series. And what you can see here is where we ended up, which was we have a trained decision tree using some features that we have selected based on various data analyses that we conducted earlier in the video series to find variables that seem to be very predictive about which passengers on the Titanic survived and which ones perished based on the data set that we got for the Kaggle competition. And I'm not going to drain this because you can go back into video 6 if you'd like to get more details, or if it's been a while since you've seen video 6, you may want to at least watch the last chunk of it. It's a pretty long video, and to refamiliarize with where we're at. But basically, we passed in 5 features: P-class, new title, family size, ticket party size, and average fare. We trained a bunch of R-part models, which are individual decision trees, using threefold cross-validation, repeated 10 times. We did that to ensure that we're going to get a reasonable generalization estimate of what our error is going to be for unseen data by doing that. We got the output, and I'll go ahead and just run that just for grinsies, and we can see here that at our ideal parameter for building the trees that we found through cross-validation, we're expecting, we would hypothesize that we're going to get around 83% accuracy with this model. Great. And this code here just plots it, which just shows you the graphical representation of it. Like I said, I'm not going to drain it. All right, we've spent a lot of hours together learning about data, playing with data, learning about R and various machine learning techniques. But now it's high time we actually get to the meat of the matter, which is let's do a submission to Kaggle and find out how well we did. So I'm not going to go through the actual Kaggle web UI. That's relatively intuitive and would be a waste of your time, quite frankly. But what I will show you is the code that you can use yourself if you're interested to generate a submission and get into the Kaggle scoring as a competitor. Hopefully this isn't too much of a spoiler alert, but this model actually does pretty well. So when you actually submit this code as it's outlined below, and we'll go over here in a second, and you submit it to Kaggle, you're going to score around 80%, which is not bad because we thought from our cross-validation that we'd end up scoring around 83%, and usually there's no absolute guarantee about whether your cross-validation is going to give you a 100% accurate score or not. It's a guess. It's a best estimate. And if you're within, in my experience anyway, 3 to 5% between what your CV score does and what your holdout test score does, you're in pretty good shape. And this is what we see here, which is the tree scores around, it's about 3% less. Ish, less than 3, about less than 3% less. So a little less than 3%, which is not bad. All right, so let's go through the code about how you can actually generate this submission to get this pretty good score of 80.383%. All right, so the first thing that we need to do is grab from our data.combine data frame. So that's the data frame that we've been using all along that holds both our training and test data. And this is where we've been engineering features and doing all kinds of interesting data analyses. But now we need to subset it, because now we need just the test aspect of that data frame. And that's the rows that correspond to these indexes here. So rows 892 through 1309 were the test records that we appended on to the training records to create originally this data.combined data frame. Next, we don't want all of the columns, because if we go up here, we can see data.combined actually has a lot of columns. Let's go ahead and just pull that up real quick. And here's our data.combine data frame here in the view. And you can see we've engineered some features, and there's some features that we don't really care about. For example, tickets, we found that they're not particularly useful. So we need to subset this. And this features vector, we can just go ahead and take a look at that, what that is, and say, okay, our features vector are these 5 things. Now, interestingly enough, as we talked about last time, decision trees actually implement strong feature selection, and this is what you see here. Even though we passed in 5 features to the algorithm, it only used 4 of those because these 4 were the best. Great. So we're going to pick 5 features, but that's okay. It doesn't really matter because when we do our predictions, the model's been trained to only use these 4, and it will only use these 4 in creating the predictions. Okay, great. So let's go ahead and execute that code. And you can see down here, test.submit data frame. We'll click on that and take a look at it, and sure enough, it's exactly what we expect, right? Starting at row 892, going on down, third class passenger, new title of Mr., family size is 1, ticket party size is 1, and this person paid 7.8292 pounds for their fare. Great. So now we've got a data frame of just the features that we care about for the test records, which is exactly what we want to do. So next up, we need to use a function to feed those test records into the model that we trained at the end of video 6 to create some predictions. And that's what this line of code does. So as we've seen so many times in this video series, use the help system. Now in particular what we want to do is we want to take a look at the help file for the predict function. But more specifically, there are many, many flavors of the predict function, as you can see here in the IntelliSense that pops up in RStudio. Here's one for RFE, one for RPart, one for random forests, one for REMA, so on and so forth. Now we know that we're working with RPart. That's the package that we're using to train our trees. So we want the version of the help file for predict.rpart. Makes total sense, right? That's the flavor of predict that we're interested in. And over here you got the help file for this particular function. I'm not going to drain it, but there's one thing I do want to mention because it'll be important when we talk about the rest of the function call here. And that is you have to specify what kind of prediction, the type of prediction that you want out of the RPart version of the predict function. And you can see here that there are different kinds of types. And for example, if you want this type of prediction, what this will give you is the probability. Right? This will give you the probability of the prediction. And that could be 30% or 40% or 50%, that sort of thing. And what that corresponds to is essentially, in our plots here, it corresponds to essentially these ratios. Right? What would happen is if you said, hey, give me a prediction for a female passenger in second class, it would come down and it would say, okay, well, no, it's not a Mr. No, it's not third class. So what I'm going to do is I'm going to predict this ratio, which would be 173 divided by 182, and that would be the percentage I would get back. I wouldn't get a 1. I would get the probability as calculated by these ratios. That's not what we want for the Kaggle competition because the Kaggle competition is using a 0 or 1, a class. Did you survive or not? So that's what you see up here in this code base, is that we're going to call the predict function. We're going to use the final model that we got back from our cross-validation run. We're going to feed into it this test data frame that we just created, and we're going to ask the prediction function just to return us back the class. That is a 1 or a 0. Now behind the scenes how it's doing that is it's using the probabilities that we talked about earlier. And if you wanted to just get the probabilities back and convert them yourself using something like if-else, you could do that, but it's just simpler just to say, hey, give me back the class predictions. All right. And we're going to take the output of that and cram that into a variable that we'll call rpart.3.preds for the predictions for the rpart3 model. All right, let's run that code. And let's just go ahead and pull that up. And sure enough, you can see we get a whole bunch of zeros and ones. And these are our predictions, right? Starting with row 892. and going all the way through 1309. Sweet. Now, what's potentially interesting is to say, hey, you know what? Let's just run a table command on that and get the relative counts. And what we see here is that for this model and this set of features, our predictions on the test set are about, a little bit more than 1/3 of. We predict more than 1/3 of the test records survive, as you can see here with 152 versus 266. So a little more than, 1/3 of the values. Okay, great. So we've got our predictions. Now what do we need to do? Well, we know that from the Kaggle webpage that we need to submit a CSV file with a particular format. And in particular, what we want is a CSV with the passenger ID in the first column and whether or not they survived in the second column. And what I'm doing is I'm using the data frame function to create a brand new data frame with a column called passenger ID. And what I'm going to do is populate it with the IDs, right? 892 through 1309. Simple, right? This allows the Kaggle system to actually be able to decide whether or not this prediction corresponds to what particular value. Because in theory, you wouldn't necessarily have to submit these in order because you have the ID. There you go. And then lastly, we're going to go ahead and cram in the survived. So we can go ahead and run that, and then once we create that data frame using the function, we'll cram it into a variable called submit.df. So let's just go ahead and run that line of code, and we can take a look at submit.df. Sweet, does exactly what we want. And then lastly, we can use the write CSV function to write the data frame out as a CSV file, which will be suitable for submission to Kaggle. So you just call write CSV, and as always, you can take a look at the help function. The help page for the function. So it's pretty simple. We just pass in the data frame that we want to write out. We give the file a name. Now this is just a convention that I use when I do Kaggle competitions or even my work for Microsoft. You don't have to do things this way if you don't want to. It's totally up to you. But this essentially says, look, this is an R part submission. This was the date on which I did it. So you can tell that I've been working on the content for this video for quite a while. I submitted this on June 19th, 2016. It was the first submission of the day, and of course, it's a CSV file. Now, what's important when you use write CSV is you don't want to have row names come out. If you don't specify row names equals false, what you'll get is a third column, an unneeded column in your data set, corresponding to what R figures as the row name. You don't want that, so just leave it off. Okay, now if you execute that line of code, great, you get a file that comes out, and let's just go ahead and double check that in the file system here on my Mac. And you can see our part right there, July 5th, 2016, which is the last time that this was run. And it's going to take a bit because it's slow. And there you go. Nice Excel file. Great. And we're going to get the little spinny ball. Okay, fine. Have it your way. Actually, let's just go ahead and get out of Excel here. All right. And you can see here all kinds of different submissions that I've done over the course of making this video. Okay. Video series. Great. Now, if you submit that, as I said earlier, you're going to get a score of 80%, which is not bad. But you know what? Maybe we can do a little bit better. So we've taken a look at random forests as a potential way to improve over a single tree, right? And there was some videos on YouTube that I suggested you could watch if you wanted to learn more about random forests. But basically, random forests are large numbers of trees that are built from various subsets of the training data. And the idea is that you get better predictions because you get lots of little trees that are looking at various slices and dices of the training data. And when you average them all together, it's better than just creating one single tree using all of the data. So here we go. What we want to do is subset our features out, because we know that from the plot here that individual decision trees implement strong feature selection, but random forests have a weaker form of feature selection. So we can use the learning from the single tree to help out our random forest. So what we'll do is we'll actually only put in the features that we see here were actually being used by the best single forest that we trained for cross-validation. And then we'll create a temporary data frame for training using the training data, which would correspond to the first 891 rows of the data.combined data frame, and then the 4 features that we're interested in. So we'll just go ahead and execute those 2 lines of code. And you can see RF train temp right here, 891 observations of 4 variables. Excellent. Now we've been using the same seed relatively consistently throughout this video series, so we'll do that again. And what we'll do here is we'll invoke the random forest function. We'll set the seed because we want consistently created trees every time you run that. If you didn't set the seed, you're going to get different results every time because, well, it's random forest, so it starts at a random location, and this forces the function to start in the same place every time. Okay, so we tell the random forest function, hey, here's the training data. Here are all the x's, the input to the algorithm, and here are all the y's. Or if you like, these are the dependent variables, this is the independent variable, or these are the predictors, this is the response variable, however you name it. There's lots of ways that you can talk about it. This is the features, this is the label, and we're going to use 1,000 trees. Now, one of the posters mentioned that, wow, 1,000 trees seems like an awful lot. And the answer is, for this data set and for this few number of variables, it absolutely is a lot of trees. And in fact, you could probably get away with the same level of accuracy using less trees. But for the sake of consistency, I'm just going to keep it at 1,000. So we'll just go ahead and run that code. And you can see here that the output from random forest is quite useful. First thing you'll notice is that the random forest algorithm can actually give you a reasonably accurate prediction of its error rate, or reflexively its accuracy. If you just take 100% minus the error rate, that'll give you the accuracy. And out of the box, because what happens is that because it's doing a random subset of rows and columns each time, it can train a tree with the random subset of rows and columns that it pulled out of the training data set for that tree, and then use the rows and the corresponding rows that it did not select, and then use that as a test for how well the tree performs. And that's known as the OOB, or the out of bag collection of rows. And what we see here is that the accuracy across all 1,000 trees of this technique of grabbing a subset of rows and columns, training a tree, then testing that tree against the rows that weren't selected. And then if I repeat that 1,000 times and I average it, I get approximately, this should be in the high 80s, right? Yeah, high 83, excuse me. 83 so the estimate is that I'm going to be 83.84% accurate. And then we see a confusion matrix here, which then says, okay, let's break that down based on the out-of-bag test that I did while building this random forest. And in general, I'm far more accurate. That means I have less error on predicting folks who perish than I do correctly predicting people who survive. And then when I average that together all out, net, I'm getting about 83.84% accuracy, or net 16.16% error rate. Okay, cool. Now, this should look pretty familiar to you. It's basically the same code. We just need to then pull out a different set of features here because we've subsetted the features slightly differently. So we're going to create another test .submit.df data frame from our data.combined. Once again, indexing the test data at indexes 892 through 1309, pulling out the 4 features that we care about. And there you see test.submit, 418 observations of 4 variables. Sweet. Now we can go ahead and once again use the handy dandy predict function, but as we know, there are different kinds of prediction functions. So we're going to take a look at the help file for predict.randomForest, which is the proper flavor of the predict function for a random forest. And you can see here that it's a little bit different than the predict function for rpart trees, because by default we get the type of response variable, which corresponds to the type of class that we saw in the rpart version of the predict function, which gives us the 1 or the 0. That's what we're interested in. So we don't need to pass any more parameters to the random forest version. We just say, hey, give me some predictions from the model that I just trained, which we called rf.temp. Feed into that model our test features, which we store in this data frame right here, and I'm going to go ahead and store those predictions in a variable called rf.preds. And once again, I can also run the table so we can see the distribution of the counts here. And what we see here is, if you remember from last time, whoa, that's not right. rpart preds. You can see that we have a subtle difference here. With the same features, the rpart tree predicted 152 folks survived, but our random forest is predicting 153. So there's a slight difference there between the two. And what's interesting is that, spoiler alert, as is recorded here in, and I'm no doubt you noticed already in the comments, is that this model actually performs a little bit better than the single tree, which is kind of what we would expect intuitively, right? There's a reason why you would use random forest, is because obviously there's some advantages to it over single trees, and we're seeing that here. Now, what we don't know for sure is you could certainly do this, but I would advise you not to. You could go and analyze the predictions from the rpart and the random forest trees in depth and find out which variables changed between the models and try to do some analysis on that. But you run a really big risk of overfitting when you start doing things like that, especially overfitting to the public data set. And as I've lectured at length before, what you see an awful lot in Kaggle competitions is that people build models to overfit to the public test set based on the leaderboard score. And when the competition finally ends, you see lots and lots of people drop. Sometimes quite a few places, because what happens is that their models are so tuned to the public test data that they don't generalize to the unseen private held out data, and they lose position. You see it all the time. So I would, while you could do this, I would strongly advise don't spend a lot of time analyzing the predicted output on the public test data from one model to another. It's a good way to end up overfitting. So my advice, if you want to do it, fine, but I would suggest not doing it. Okay. Enough of the soapbox. Okay. Once again, I'm not going to drain this code. We just created a submission, and then we write the file out to the file system, and you'll just run that code, and great. I won't even bother pulling it up in Excel because there's not use in that. Okay, let's flip over to Kaggle real quick. So what you'll see here is that this is the result of the submission, and you'll see that last time I submitted the random forest output was on Tuesday, July 5th, 2016, so almost a week ago from me recording this video right now. And it hasn't changed at all. It still puts out a score of 80.861%, which right now is good enough to put you in the pack here of folks in, you'll see there's a lot of people that have a similar score. which probably tells you a lot about the nature of how much you can really do with the data. And then here's a bunch of 8383s, which is what we got with our R-part tree. But you'll see here that if you get a score of 0.80861, you're going to get at least in around 414. I'm up a little bit higher, probably because of just timing. Because you'll see there's a bunch here of folks in the same spot. But the point of this is that out of 4,283 teams, our very simple model of only 4 features puts you in the top 10%, which is pretty good. I mean, that in a normal Kaggle competition, top 10% is a badge. Actually, top 25% is a badge, and top 10% is an even better badge, which is great. So this shows you the efficacy of the model. And the other thing that's probably really important to realize is I would bet that when this competition closes, and I don't know if they do this anymore, but they used to for the Titanic competition, and then they evaluate the model submissions against the private holdout, you'd probably go up because a lot of people up here have no doubtedly overfitted to the public data set, and they will drop when against the private data set, the unseen data that that Kaggle holds out. So, gist of it is pretty cool. For a pretty generalizable model, we're in the top 10%, good accuracy, competitive model, and in the end analysis, we'd probably end up being even higher up in the stack ranking because of people having a tendency to overfit to the data, and our model will be less likely to do that because we've tried very, very hard to avoid overfitting. Okay, great. But let's say, for the sake of argument, that you're a real go-getter and you want to do even better than that. Okay, so the question would be, okay, Dave, that's fine. Thank you for teaching me all this good stuff, and I love it. But you know what? I want to be even better in terms of the end analysis and the end stack ranking. So what do I do next? Well, a good rule of thumb is to say, look, you know what? The best way to improve your model is to start looking at places where it gets things wrong, quite frankly, in the training data, and see if you can actually do some feature analysis or apply some other techniques to say, look, are there ways to improve my model where it's not doing well? And then in our case, this is a good way to start that analysis, to say, okay, and I alluded this earlier, or maybe I didn't, excuse me, is to say a good place for us to start is where we tend to get things wrong most often. And this is the glaring place where our model is exceedingly pessimistic, right? There are 86 records. It's by far the single biggest chunk of records that we get wrong. And that is for adult males. We just don't have good features to understand how to determine whether or not an adult male was more likely to survive or not. So the question is, well, how do I start talking about that? How do I start thinking about that? Well, you could do what we've done before. You can start engineering new features, start doing the various plots that we've looked at in the video series, and that technique is well and good, and obviously I spent a lot of time covering it for precisely that reason. But what I wanted to finish up this video series with a couple of other techniques that you can use to help out. And if you go to YouTube and you search on feature engineering, there are tons and tons of videos on YouTube about feature engineering, or if you Google it, lots of articles about feature engineering. So it's a broad subject. You can spend lots of time doing it, researching it and practicing new techniques. Totally advise you to do that. I'd figure I'd put a couple more tools in your tool belt. Not saying these are the best tools, or not saying these are the only tools. They're just a couple of tools. Okay. So the first thing is that you can look at is a concept that's known as mutual information. And you can think of mutual information as a mathematical way of understanding if features that you've engineered or features that you have are potentially useful in terms of prediction. So I'm not going to drain, obviously, what mutual information is. You can take a look at the wiki pages for mutual information, and we'll also be looking at conditional mutual information as well here in a minute or two in the video today to get some higher level background. A really good page that I found that actually talks about mutual information in a relatively intuitive way and actually and puts it in the context of feature selection is a page here from Stanford. They have a really good book on information retrieval, and this is a particular page out of that manual. So here's the URL. Obviously, you can pause the video if you want to get the URL, but it talks quite a bit about mutual information in terms of using it for feature selection, and that's exactly what the context that we're using it for in today's video. Closely related to mutual information is this concept of entropy. So here's the page on entropy. Lots of good resources on it. Okay, cool. All right. There's a package called InfoTheo, which stands for information theory, that you can install and load up, and that provides some handy-dandy functions around mutual information that you can use, and that's what we're going to do. Now, the easiest way to think about mutual information is like this. I can compare two variables, and I can say, look, if I have variable A that I'm trying to predict, and I have variable B that I think is associated to variable A in some sort of predictive capacity, what mutual information allows you to do is calculate a metric based on information theory to tell you how much more you know about variable A if you know variable B. And we saw essentially the same concept earlier in the video series in our visual analytics. For example, when we're doing bar charts and we say, okay, hey, if I know P class and I know survival, what are the relative colorings of the bars between first class, second class, and third class regarding survival? So for example, we saw in general that especially if you were female and you were in first class, your bar had a lot more survival in it than not. And that told you that the variable of P class and the variable of gender give you a lot more information about predicting survival or variable A. And I know that's not super intuitive, or maybe it is super intuitive. But I think going through some code will actually, give you some, higher, some better intuitive grasp of what it is. And of course, you can go do lots of research if you want to understand the math and the theory behind it. I gave you a couple of places to start. Okay, so what we've got here is a function called mutinfo, which stands for mutual information, and of course use the help system, and it'll talk about it. Now, what we're trying to do here is just to get some sort of sense of mutual information. Let's go through a subset of the features in data combined and say, okay, you know what? How good are these variables in terms of mutual information vis-a-vis our survived label, which I'm just using the RF label variable here because it has the various survival labels that came from the training data. And what this allows me to do is just evaluate each of these variables one at a time. So let's do the first one here. So what we're going to do is we're going to say, look, if all I knew was P class, the class of the individual, how much information does that provide me around survivability? And the way we interpret that in predictive modeling is, how good of a predictor is it in general? And I won't go into the actual nature of the metric because you can read up on nats versus bits and all that kind of stuff. For our purposes, what matters is the higher the number, the better, essentially. And what we see here is we got 0.058 for P class, and if we do it for sex, it gets quite a jump. And that makes intuitive sense for us, right? We already looked at that throughout the video series as embodied by the title. We knew that title was a compound feature that incorporated information regarding both gender and age, and we know that that was a significant predictor. So by extension, we would think that gender or sex is also highly predictive. That is, it would have a lot of mutual information with the survived label. And what we see here is that, in fact, yes, it does. It has approximately 3 times, well, 2.5 or so, maybe more than 2.5 times the mutual information with the survived label than does just whether or not you're in first, second, or third class. Now, we can run a few more. So we can do SIBSPA and Parch. And as we found, we didn't find SIBSPA and Parch to be particularly predictive. And intuitively, we would think the mutual information would also be low. And that's exactly what we see here. I do want to call out something that's pretty interesting here, and that is the different call between these variables, which are all factors here, versus, or I should say, these are all discrete variables. They happen to be factors, but they're also discrete, meaning they take on fixed values. Whereas fair is a decimal number. It is not a discrete number. So what we need to do to use the information function is use a function called discretize. So let's go ahead and pull that up in the help system. And all this essentially does is it takes a non-discrete value and bins it for you into a bunch of discrete values. And you can read more around which algorithms it uses and which trade-offs you can make in terms of how the bins are created. But generally speaking, my experience has been is that the defaults work pretty well. So what this does is takes a non-discrete variable, which is the fairs, turns it into a discrete variable, and then we say, okay, calculate the mutual information between it. Now, intuitively, we would expect fair to be reasonably predictive because we know that average fair was a variable that we selected in our R-part tree. So an average variable is related to fair, so it's correlated to fair. So we think that there would be some predictive value there. And as you can see, sure enough, far more than SIBSPA or Parch, and even more than P-class. So that's intuitive. All right, so I'm not going to drain the rest of this. Let's just go ahead and run the rest of them down. Okay. And this output should be pretty reasonable and intuitive to us. So title, which was one of our first very highly predictive variables that we engineer, is even better than gender because it also, as we know, incorporates age. And we didn't use age directly because there was lots and lots of missing values. So we used title as a proxy for age, and we found that to be pretty effective. So not surprisingly, the mutual information between title and survived is even better than just sex by itself because it has the added information of age in it. And down here we can see that out of all the features that we've engineered or looked at, that new title is the top dog. Because as we saw in the previous video, we went through some trouble to clean up the titles, and we consolidated a bunch of titles together, and that's bearing fruit, not only proved out in terms of the results of our model training, but also in terms of mutual information. Now, one thing that's important to mention, and maybe you intuitively recognize this already, is that there is a strong correlation between the way trees, the tree algorithms, train themselves based on data input and mutual information. For example, you can actually train trees using entropy-based methods, and as you saw before, entropy is related to mutual information. So there's your conceptual tie. Things like using Gini, the Gini index, for example, is also conceptually related to mutual information. So the reason why I bring it up here is if that you're planning on using tree-based methods, which why not? They're very commonly used in Kaggle competitions as well as in real-world situations for lots of valid reasons. Mutual information is a good way to do some validation on your feature engineering efforts because it gives you a lot of insight into how the features will potentially perform in your tree-based models once you've trained them. It won't always be one for one, it won't always be 100% accurate, but it's a good yardstick to use in your feature engineering efforts. Okay, so you can see here that in general, we've got a few standouts, and they tend to be related primarily to sex and age. And if we actually took the time to impute age, which we shied away from because of the large number of missing values in this video series, although some folks on the Kaggle forums will tell you that they've had success with that. And you can take a look into that if you'd like, certainly for your future efforts if you're interested. If you correctly or accurately imputed ages, you would probably expect that age to also have a very high mutual information, because we kind of know that based on our analysis of title that age and sex are primarily the most important features that we found for predicting who survived and who did not on the Titanic. Okay, so there you go. Mutual information, good way to explore potentially using tree-based mechanism whether or not a feature that you've engineered or a feature that you have is likely to be predictive or not of your label. And this can augment visual methods. Now, you may be asking yourself why I started with visual methods and didn't do mutual information first. And the answer is that, quite frankly, as visual creatures, human beings, we're much, much better at detecting patterns and subtleties in data using visual mechanisms than we are even using mathematical calculations. So I highly advise that you always start with visual analytics. If you're familiar with the space, there's a reason why tools like Spotfire, Tableau, and Power BI are very, very popular and very, very useful. It's because human beings are visual creatures. We're very, very good at pattern recognition using visual media. So that's why you should start there. But here's another tool in your tool belt, mutual information. Okay, great. Well, to wit, on my exposition on human beings being visual creatures. There are various techniques for reducing the number of dimensions that you have in a model or in a data frame to allow you to do different things with them. We haven't talked a lot about dimension reduction in this video series because it's a relatively advanced topic, and given the kinds of models that we use, tree-based models, you don't really need to do a lot with dimension reduction. Generally speaking, to help them out in terms of their performance, they're pretty good. Dimension reduction is very useful for various linear techniques. For example, if you're doing a regression, for example, if you're using just straight up linear regression or polynomial regression, a lot of times you can get some uplift by doing dimensionality reduction using things like principal components analysis or PCA. There are many algorithms for doing dimensionality reduction, and the easiest way to think about that is think of our model here. And essentially, we are using 4 features or 4 dimensions to bucket whether someone survives or not. What's their title? What's the class of their ticket? What was the size of the party of their ticket? And how much did they pay on average for people in their party for their tickets? And if you want to think about this in geometric terms, you could visualize this as a 4-dimensional space. Now, human beings obviously aren't very good at visualizing anything other than 3 dimensions or below. So one way to think about this potentially is a 4-dimensional space is to think of it as a series of cubes. So for example, you could imagine a cube or a 3-dimensional space where P class was the x-axis, ticket party size was the y-axis, and then the average fare was the z-axis. And then what you would do is you would actually have a collection of three-dimensional spaces. And let's do levels data dot combined new title. And you can see here that in the new title, we could then have 1, 2, 3, 4, 5, 6, 7, 8, 9 of these three-dimensional graphs. So if you close your eyes and you imagine a chalkboard drawing of a three-dimensional space with x, y, and z coordinates, and then imagine, if you will, a really big chalkboard with 9 such graphs, each one corresponding to one of the levels of new title. And that is one way to visualize a four-dimensional space. And that's kind of complicated. And as you might imagine, if you had a fifth dimension, now you would have to have 5 chalkboards, or I should say 5 chalkboards. You would have multiple chalkboards, and each chalkboard would correspond to a value in the fifth dimension, and so on and so on and so forth. So it gets really complicated, very abstract, really fast, right? And it's hard for human beings to work with that. Not only that, but as you get more and more dimensions, you get what's known in the machine learning space as the curse of dimensionality. You can Google that if you want to learn more information about it. But basically what it means is that as you get more and more dimensions, things get more and more problematic. For our purposes, what we're interested in is doing some dimensionality reduction so we can do some visualizations. And this can be a very powerful technique for kind of understanding what's going on with your data, especially as your dimensions increase. And if you decide to go further on your own with the foundation that we've laid here in this video series for feature engineering, you're probably going to end up with models with more than 4 features. So maybe you can visualize the chalkboard that I talked about pretty easily, right? A set of 9 three-dimensional graphs on a chalkboard, right? That would be your 4-dimensional space. Okay, maybe that's pretty easy, but when you start talking about 7 or 8 dimensions, which is not that many dimensions actually for a modern machine learning model, it breaks down pretty quickly. So the idea is, as human beings, how can we overcome our limitations? And there are various mathematical techniques that you can do for that. One of them is an algorithm known as TSNE. I won't go into it. You can Google the RTSNE package and you can find out more, and then that'll give you even more references, or we can just load it up as well and hit the help system. Dave, why are you not following your advice? And there's usually some references, right? So you can go look more about it if you want. So essentially, RTSNE is a dimensionality reduction. And what we're going to do is we're going to use this to illustrate a 2D representation of our 4-dimensional space. So it can kind of show you in geometric terms, where there are clusters of folks that survived or did not survive. And then what that allows you to do is to say, look, as I go to more and more dimensions, the visual techniques that we've learned so far become quite complicated. In ggplot2 terms, how many facet wraps can I really actually do in a single plot? And because facet wraps allows us to combine multiple dimensions at the same time, so we get higher dimensional representations, but that'll break down at some point. So what this allows us to do is to create an artificial projection from a high dimensional space to a lower dimensional space. In this particular case, it'll be a 2D space. And that'll might help us out in terms of visualizing what's going on with our features vis-a-vis our predictors. Okay, so let's start with an area of the model that we know we do pretty well on, which essentially is this part of the tree, right? Essentially, anybody who doesn't have a title of Mr., we tend to do pretty well on. So what we'll do here is we'll subset our data to say, look, give me a new data frame called most.correct. That essentially is any record in the data.combine data frame that doesn't have a title of Mr. And then what I'll do is I'm also going to get the indexes out of that newly created data frame that corresponds to our training set. That is, hey, give me every label that isn't none, because none was the default value that we provided for the train data. Okay, so let's go ahead and run that. And the next up, let's go back to help. We're going to run the RTSNE function, RTSNE function. Sorry, I'm really butchering that. In general, the defaults work pretty well. You can go ahead and play around with the various parameters on the function if you'd like after you check up on the help system. But I tend to find that the defaults work pretty well for the purposes of what we're using here. So we'll go ahead and run that, and you'll see here what we're going to do is we're going to only pull out the features that we care about, the 4 features that we care about, out of the most correct. This is kind of important. By default, the algorithm, the function, throws an error if it finds duplicates in the data. And literally what it'll say is if you have an observation that has the same values for all 4, I don't like that. So that doesn't work for us because we know for a fact that we're going to have multiple people with the same title in the same class, probably with the same party size, and probably with the same average fare. That's likely to happen. So we said, look, you know what? Don't check for duplicates. Turn that off. Okay, great. All right, now this algorithm takes a little bit to run. It's not hugely computationally intensive, but it's not instantaneous like we've seen with some of the other methods that we've used based on this small data set. All right, so now what we've done is we've executed the function, got a return value, and stored it in this variable that we're calling tsne.1. And we can plot this. And what we can plot essentially is a part of the return tsne.1 variable known as y. And y essentially, you can think of it as essentially as a 2-column matrix, or you could literally think of it as a collection of xy components. And that's probably the most intuitive way to think about it. So what we're doing here is we're creating a 2-dimensional plot with ggplot2, and we said, hey, look, for the x values, grab from this return object here the y component, and only grab me the indexes that correspond to the training data, and give me the first pair, the x values. If we think of each row in this object as xy coordinates, and we can check this out for ourselves here using the dim, and we can see, oh yeah, sure enough, there's 527 rows and there are 2 columns, right? So we can actually look at this as a two-dimensional matrix of xy coordinates. So what we're saying is, okay, grab me all 527 of the x values, and then grab me all 527 of the y values as indexed here by 1 and 2. And then I want you to color code it based on whether someone survived or not. And then just create a dot plot. So let's go ahead and just visualize that because it's pretty intuitive. And let's zoom into that. And here's what we get. So what we've done is we've taken this 4-dimensional representation of P-class, new title, party ticket size, and the average fare, and condensed it down into a 2-dimensional representation, and then color-coded it based on whether people survived. And what we're looking for here are clusters of similar colored dots. Because in general, the more cleanly these turquoise colors are separated from the orange colors, the more likely it is for a machine learning algorithm of any kind, and in particular trees, because they're very good at identifying nonlinear boundary areas, makes it more likely that they're going to be successful. And we know that we're pretty accurate in general for folks with titles other than Mr. And now we can kind of see why in one single all-up relatively intuitive view. Because we can see huge tracks huge areas where things are predominantly one color or another, right? So down here, holy smokes, only, now some of the dots may be standing on top of each other, but let's just say for the sake of argument that they're not. Holy smokes, there's only 2 orange here. So if we're down here in this area, conceptually, we're just going to predict that you survive, and we'll be accurate quite often. Similarly, there's a whole bunch right here in this whole area right here, right? If you start here and you go down over here, or even if you cut it real close and you shave these in and you go over here, pretty accurate, right? You're only talking about 1, 2, 3, 4 out of all these dots. And up here, hey, this cluster, wow, you predict, or if you go, what, collect these in, then wow, pretty good. So this gives you another tool in your toolbox to say, look, as I get more and more complicated in my feature engineering, how am I doing? Now, of course, you still need to validate anything, even if you, let's say you use 10 features and you create a 2D visualization and you get the most perfect separation with like all orange up here and all turquoise down here, you're still going to want to run your cross-validation because that may be endemic of overfitting, right? So you always keep that in the back of your mind, right? Even if this thing is perfect, well, actually, to be honest with you, if it is perfect, that should be sending off a warning bell in your mind that, in fact, ooh, I'm probably overfitting. Always, always, always assume that you're overfitting. When things are going really, really well, be fearful that you're overfitting. Okay, cool. All right. Now that being said, let's take a look at another potential tool in your tool belt, which is conditional information. Now, mutual information is essentially one-for-one. Hey, I've got a predictor variable, which we'll call A, and I have a potential feature called B. If I know B, how much uplift does that give me in terms of my understanding of A? Or another way to think about it is, how predictive is B for A? Now, what conditional mutual information allows you to do is to actually use A, B, and C. So if I know B, and then if you give me C, does C give me even more uplift regarding predicting values of A? And you can think of this is analogous roughly to some of the facet wrapping that we did. So facet wrapping, so a bar plot allowed us to essentially do a two-dimensional view into the data. When we facet wrapped, it allowed us to do a third dimension. Facet wrapping could also allow us to do a 4-dimension because we could just tack on things. But our early facet wraps allowed us to do essentially something very akin to conditional mutual information, which is allow us to say, look, if I have 2 features at the same time, how much more predictive is that vis-a-vis the survived label? Okay, so the function out of InfoTheo that allows you to do conditional information is conned information. And you can see here we're just essentially doing the same thing. We're saying, okay, look, give me out of the most correct data frame, give me the survived label for the training indexes, and then I can grab the y values from the TSNE variable that we got back from the call to the function. Just grab me the indexes for the training data and grab me both columns. Now these are real value numbers, right? They're non-discrete, so we'll discretize them. And then what this does is this returns me back a matrix of 2 columns, and that allows me to say, hey, look, if I have 2 discrete representations of these x, y coordinates, how good is that at predicting the survived label, right? Essentially, this is the mathematical representation of how cleanly the turquoise is separated from the orange. That's the way to think about it. And we get a pretty high number, 0.2649. Now, if you recall from last time, our highest single mutual information was title, and when it was a 0.17-ish. So this is quite a bit higher. Well, that's cool. Now, we can compare how good this 2-dimensional representation is at providing information regarding the turquoises versus orange. Or another way to think about it is how good are these two values at cleanly separating the turquoise from the orange by comparing it to the conditional mutual information to two of our features, notably, let's say, for example, new title and P class, because we know that that was in our model here, right? First thing we looked at was new title, and the second thing we looked at was P class. So let's say, hey, you know what? What's the mutual information between these two things? Conditional mutual information between these two things. If I run that, it's pretty high. It's 25, but it's not as good as the two-dimensional representation. And that should match our intuition, because essentially this 2D representation, as embodied by these x values and these y values, incorporates more than just these two. It incorporates the additional information of these two as well, right? So it should do better than just these two in isolation, because it's trying to incorporate all four of these things. Great. Okay, so now that we've got that as a mental framework for taking a look at things, let's go ahead and take a look at where we do poorly, which is anywhere where you have a title of Mr., our model just predicts that you perish, and we're wrong 86 times, which is not too good. Let's see, what is the percentage of that? Just so that we got, some idea here. Well, that's not going to work. Okay, here we go. Nope. Sorry. Okay, so our error rate here is 16%. So that's not too good, right? That reflexively, that's an 84% accuracy rate. So there's a lot of room for improvement there. Okay. So similarly, what we'll do is we'll subset a new data frame called Misters from our data.combine, where the titles are Mr. Great. And then again, we'll grab the indexes of which records out of Misters corresponds to the training data. Cool. And then once again, we'll run a TS and EA calculation on that using the default, which is 2 dimensions. Now you could do 3 or 4 dimensions. The problem, once again, is visualizing anything beyond 3 dimensions is pretty difficult. R does have facilities for doing 3 dimensions, but I'm just using 3-dimensional visualizations, but I'm just concentrating on 2 dimensions. I'll leave that up to you if you're interested in going 3. So let's go ahead and run that. And once again, of course, we're turning duplicate checks off because we fully expect it's possible that we'll have duplicate observations in our data. And once that runs, it'll take a little bit longer. Okay, good. We can now plot, once again, everything with misters, right? So we're plotting the x values, the y values, and then we're color coding based on the mister survival labels in the training data. Okay. Now this, not surprisingly, but boy, this really pops at you. Well, it's no wonder we just predict that if you've got the title Mister that you're not going to survive, because if you look at most of the clusters of values here in this 2D representation, the vast majority of clusters are predominantly orange. The only place where it even gets even close to maybe even 50-50, and it's probably not even 50-50 based on this, is this area over here. So this is a nice graphical representation of saying, wow, okay, if I'm really going to improve my model, especially as it relates to observations with the title of Mr., I got to get this more cleanly separated, right? I got to get better clusters of turquoise, and ideally those clusters of turquoise need to be the more far away they are, the more removed they are in this 2-dimensional space, the better. So this is one way of iteratively checking out how well you're doing from a feature engineering perspective using a graphical medium. Okay. And once again, let's go ahead and just run a conditional mutual information score on these things. And as we can see, intuitively, it's only a 0.09, whereas for non-misters, it was over 0.26, right? So this is, what, 2.5 times worse in terms of conditional mutual information. And, you know, there you have it. Okay. Last thing I want to finish up with is you can actually use the features from TSNE in your modeling. So here's an idea. What if we use TSNE to create new features for all the training data and actually use them in our model? You know, we'll just try it out, see what happens. So I won't drain the code because it's pretty much the same pattern that we've seen before, right? Let's just go ahead and create a new visualization. So this is the TSNE 2D visualization for all of our training data. And we can just add the x coordinates and the y coordinates as new columns to the data.combine data frame and see if they actually are useful. And this will take longer, of course, because it's even more variables. Okay, there's visualization. Okay, it's pretty complicated, right? It's not nearly as good as we saw as for just non-misters, but we kind of expect that, right? Because we're going to have the misters mixed in, right? And some of these clusters should look reasonably familiar to you based on the plot of misters. So we've got more complexity here, right? Not as clearly separated clusters or areas of turquoise versus orange or orange versus turquoise. Now, one thing I should mention, which I didn't mention earlier, and I apologize for this, is that we want to calculate the values for the entire data set, right? We want to map these projections for both the test and training data, but when we evaluate the graphics, the visualization, we're only using the training data. And the reason for that is consistency, right? We want to map the entire collection of our features, both training and test data, into the same two-dimensional feature space. Because if we don't, it's not going to be an apples to apples prediction when we actually run the test data through a model if we train using any of these TSNE features, right? So you want to, it's the same reason why we created a data.combine data frame in the first place. We want to make sure that any global sorts of feature engineering that we do is rationalized across both training and test set. So that's why we create the RTSNE, we invoke RTSNE on the entire data.combine data frame, but when we actually look at the visualizations from an analytical perspective, we're only looking at the training data. All right. So you can see here, the next up, we can now say, okay, you know, that's actually not wrong, or not correct. Ignore this. I will change this comment before I upload the code to GitHub to make this actually a correct comment. And then what you see here is how we can now use these features. Add the TSNE features to our data frame for use in model building. And you can see here, in general, this actually is a pretty powerful feature. So what we've done here is we've said, okay, look, how powerful is the TSNE features all up against the survive variable, right? So that's for adult males with a Mr. title, children, females, first, second, third class, everybody, right? And it's actually a pretty good, conditionally, it's a pretty good feature. It's, you know, 0.199. So it's probably worthy of adding to the mix in terms of any future efforts around improving our model. And you'll see here, lastly, the code to do just that, right? This adds in 2 new variables to our data frame, data.combine data frame, for the x and y coordinates in our two-dimensional space. And there you have it. I'm going to go ahead and leave up how you actually do the modeling and see if these features actually add anything, because we don't know for sure if they actually will add anything to you as an exercise to be done offline. So there you have it. This is the last video in the series. Hopefully you've enjoyed it. Hopefully you found it useful. I've had a lot of fun making this video series. Stay tuned to my YouTube channel. I'm going to be switching gears here, I think, in the future, trying to go to a smaller videos, more compact. And lately I've been focusing a lot of my efforts on the analysis of event logs, which I think for a broad class of people are actually potentially useful. So maybe not so much around model building, but essentially saying, hey, I've got event logs coming from my web server, I got event logs coming from my IT systems, I've got event logs from Internet of Things, from devices out in the field. How do I just make sense of this data, right? Modeling is a kind of a pretty advanced application of data science to event log data. How do I just get my arms around what do I have, and do I even know if it's even valuable or not? So I think that's going to be my next series, is event log analytics. And we're going to be looking at a lot of data analytical techniques that are really relevant for folks who have a lot of event log data and they just want to know what they've got and is it valuable. Okay, there you have it. Until next time, happy data sleuthing.